Hi everyone, I'm Dragos, and today I'm going to talk to you about bf4, our tool to ensure bug-free P4 programs. In the beginning, there was P4, and P4 promised programmable network data planes to be fast, flexible, safe, and easy to use. However, it turns out that writing P4 code is actually not that simple. Furthermore, recent verification tools uncovered bugs in P4 programs. And by bugs, we mean undefined behaviors, such as invalid header accesses, array indices out of bounds, and undefined forwarding behaviors. Automated verification tools have been proposed to aid programmers read their codes of bugs. There are essentially two approaches to P4 verification. They both attempt to answer the same question: does my program exhibit any bugs? The approach taken by Vera and P4 Node answers no more often than in reality, whereas the approach taken by P4V and the third P4 answers yes more often than in reality. We say that it has false positives. Okay, this sounds great. However, verification tools exhibit their own caveats. Intrinsically, Vera and P4 Node are incomplete. This means that they provide no global correctness guarantees. This is because they only check correctness in terms of some table entries provided to them by the programmer. On the other hand, P4V and the third P4 assume all table entries are actually possible. Well, not all table entries are actually possible. So the tool will report more bugs than are actually feasible in reality. It is now the job of the programmer to write code annotations in order to rule out infeasible table entries. Alas, writing code annotations is a difficult task. Sometimes it may even be infeasible, since the program which populates table entries may not even be known at compile time. It would be great if we could ensure bug-free P4 programs without having the programmer provide annotations nor an exhaustive list of table entries. This is the goal of our tool bf4. Here are the main ingredients behind bf4. First, a static verification part, similar in nature to P4V, checks for reachable bugs. Then it computes a set of annotations, which rule out some of these reachable bugs. For the remaining bugs, bf4 computes data plane code fixes. The resulting annotations are converted into checks, which are then enforced at runtime. I'll dive into each component at a time, starting with the static verification part. Let me briefly show you the high-level steps of every P4 verification tool and also bf4. First, the program is instrumented. Here's an example. Table nat does source address translation, takes as input the IPv4 source address, and rewrites it to a new value using action do nat. Now, what happens if there is no IPv4 header present at the moment of calling action do nat? Well, the standard clearly mandates that this is an undefined behavior. So in order to capture this situation, we need to add an instruction before the possibly buggy instruction. In our case, the if statement reads, if there is no valid IPv4 header, then go to a buggy state and stop the execution. The instrumented program is then converted into a control flow graph, which is further optimized using some compiler optimization techniques. And then we generate a verification condition, which is essentially a formula that describes the inputs which trigger an undefined behavior. We then feed this formula into an SMT solver, in our case Z3. And if it replies satisfiable, then there are indeed reachable bugs in the program. Otherwise, we deem the program correct. Let's zoom into table nat. Assume these two table entries. The rule in green works fine, since no packet which hits it triggers the undefined behavior. However, the rule in red is buggy, and furthermore, for all packets which hit it, they will trigger the undefined behavior. So clearly, no controller should ever insert such a rule at runtime. To handle this situation, we generate a filter to block this type of table entries from ever occurring during runtime. Previously reachable bugs, which have become unreachable due to these automatic annotations, are controlled. The key observation is that in practice, a large portion of reachable bugs are actually controlled. So how about the remaining uncontrolled bugs? This brings us to the second ingredient of bf4. Let's take an example. Table IPv4 LPM does longest prefix match against the IPv4 destination address. It then forwards the packet onto a given port using action do forward. Action do forward also decrements the time to live field. What happens if there is no IPv4 header? Well, same as previously, an undefined behavior will be triggered. Now assume this table entry. Clearly, there are packets which hit this entry and will trigger the undefined behaviors, and there are packets which hit this rule and won't trigger the undefined behavior. So what's missing to rule out this non-determinism? Well, actually, it's the IPv4 validity bit. Let's add it to the set of keys in table IPv4 LPM. Here's what the table entries look like. The rule in red, however, is buggy, and for all packets which hit it, they will trigger an undefined behavior, so no controller should ever add them. But this means that the bug has now become controlled. So, the key idea to handling uncontrolled bugs is to convert them into controlled ones by simply adding the missing keys in the table. Okay, now that I've shown you how to compute filters and how to compute data plane code fixes, I'll now switch to showing you how to put them to good use and ensure no bugs can creep in to P4 programs at runtime. Here's the high-level picture of a P4 pipeline. Its main programmable blocks are tables. Table behavior is dictated by means of table entries. And table entries are populated by an external piece of software called the P4 controller. So to ensure that no bugs can creep into the P4 code, we intercept every table update coming in from the controller and check if the resulting state is compliant with the specs inferred by bf4. If it is, then the change is allowed to go through, otherwise an exception is thrown and the controller must deal with it. What makes this work is the fact that specs inferred by bf4 are small enough to be efficiently checked at runtime. In our paper, we thoroughly describe the baseline algorithms to compute filters, data plane code fixes, and many other features and optimizations. I'm not going to go into the details. I just want to show you some results we've got with bf4. First of all, bf4 is implemented as a P4C compiler backend, with full support for the v1 model and partial support for the TNA and PSA architecture. For switch.p4, our largest program, we found that out of the initially 155 reachable bugs, we end up with only 55 reachable bugs after just computing the missing filters. We also end up with 23 missing keys. If we add all the missing keys inferred by bf4, we end up with no more uncontrolled bugs. All these steps, inferring filters, fixes, and checking program correctness, takes around 4 minutes. I'll now wrap up my presentation. I've shown you our tool, bf4, which uses a mix of static verification, data plane code fixes, and runtime testing to ensure bug-free P4 programs. bf4 is open source. You can find it here. With that, I thank you for your attention and looking forward for your questions.
Great, thank you for the excellent talk. People who have questions can post on Slack. but I will start with, oh, great. We have one question coming in from Hangzhou. His question is, can bf4 verify stateful P4 programs? For example, checking if a P4 program works correctly with a sequence of packets. Dragos, please.
Yes. So first of all, thank you for your attention. No, at the moment, bf4 is not capable of checking multiple packets. So basically, it cannot keep state from one execution to another. This is, let's say, sort of a more principled limitation, which lies in the fact that it can only check, let's say, a number of unrollings of the loop. One workaround to check these kind of properties would be to sort of add multiple instances of the program, one after the other, and then try to check for some properties in this way.
Great, thanks. The next question is from Nan Zhai from Alibaba. His question is like, it seems all the examples showing the talk is mainly focused on invalid header checking. So the question is, does it help identify bugs like functional correctness? Does it handle this kind of functional correctness bugs?
So, in principle, there should be no, let's say, no principled reason why you should not be able to add custom assertions. But for the moment, the current implementation of bf4 focuses on these undefined behaviors. But indeed, we're planning to add the support for richer kinds of bugs in the near future.
Okay, so a follow-up question, like from other people, is like, is there some special bugs you expect that will be fundamentally hard for bf4 to handle, or it's really aimed to cover all kinds of bugs?
No, there are bugs which are let's say more difficult to, which are sort of close to impossible to capture. One of them is this let's say somehow forcing the P4 the verifier to check for these egress spec not set bugs. So we are capturing them, and in principle we have a heuristic to sort of add a fix whenever it sees this kind of bugs. The reason is it's simple to stop things from ever occurring in a packet. It's harder to say, okay, these things should always occur, because this means that it has to reason across all the paths through the control flow graph and say, at some point, something has got to happen. And this will yield a very hard to check formula at runtime, and perhaps it will be even infeasible to do so.
Okay, so we've done with questions about the bugs we can find. There's a few other questions about the executability of the pools. So the first question is from Yanjun Wang. He's asking, how do bf4 infer the annotations for verification? Like, it seems you need some annotations for the verification, and
yeah. Yes, so essentially the algorithm is to infer these annotations is presented in the paper. Essentially, what it does is that it attempts to find formulas in terms of table entries. So basically, we split the variables between packet variables and table entries, and we try to compute a formula in terms of table entries in such way as to never preclude, never rule out good things from happening. Because doing so, we lose no expressiveness of the initial program. So that's the best bet you can get out of inferring annotations.
Thank you. One last question, which is, it seems your fixes may add some keys to the tables. Do you worry about that increase the resource usage in the data plane and causing problems?
Yes, sure. Definitely, adding extra keys is a strategy which will, of course, increase the usage in keys in the width of the tables. So, but it's just one bit, so the width may not be a problem. However, it may turn out that you're going to have an increase in the height of the table. Basically, in the worst case, for each entry, you will end up with 2 entries if you add 1 key. But this is rarely the case. So you can essentially add this validity bit as a ternary match, and then for most of the actions, you will end up with just one. And then for the remaining ones, only for the buggy ones, you will get two of them. But anyhow, there is indeed a need to investigate further on the actual impact of adding keys to the P4 program. Yes.
Great.
All right. Thank you. And I apologize for mispronouncing the title, bf4, not bp4. So we'll take questions both on the Zoom Q&A if folks are there and want to post questions, or on the SIGCOMM 2020 TS4-verification channel on Slack. So we have a question from Slack. In the switch P4 evaluation, where did the control plane entries come from? Are they from the open source control plane programs, or did you write them by hand? And please go ahead and unmute yourself. Yeah, great.
So for the control plane evaluation part, the entries we used are essentially randomly generated. Right? So they're not taken from the Sonic or from the SI switch. They're just randomly generated just to test the things we were trying to isolate.
Great. I have another question. So, one of the cool things about P4 and why it's kind of a rich language to look at is it combines a simple data plane with sort of these holes where the control plane can reach in. And so, that's where there can be some flexibility that can be hard to manage if you're trying to think about correctness, because you sort of don't know what the control plane will do. And so bf4 is sort of narrowing down that interface, constraining that interface to avoid bugs. Do you have any thoughts on how the language design might evolve to better express the properties that control planes need to know about and data planes need to know about and they need to work on together?
That's a really interesting question. I guess that one way to put it, sort of, now you can sort of express these undefined behaviors. You can add these filters, which is fine. But also handling higher level properties will be trickier. I guess that even though we argue for automatically inferring annotations and stuff like that, certainly there is still room to add annotations or some sort of way to add to pass information from the switch, from the P4 world to the controller. I guess that they could be essentially converted into checks. I don't know, just code generation or any other strategy by means of just in the way that you generate the stubs for the server in P4 runtime. You can also generate these checks automatically, I guess.
Great. We have one more question from Slack. I guess the comment is that verifiers are never fully automated. So what about the limits of the approach? Is there anything inherent or any scalability issues that you foresee?
Yes, so in terms of limitations, so essentially this tool is limited to inferring stuff which can't be there, right? Trying to say things like there is an entry which should always happen at some point. Let's say that you say, I'd like to have the packet sent out on a port, so the egress spec set on all paths. So that's something you can't really reason about. You can't really say that you generate a huge formula in principle. So for that, we are using heuristics to just have this set the default drop and then pass through the pipeline for this egress spec. Other limitations include the properties we are managing to check. Just safety, these are safety properties. We're not handling stateful things or other temporal logics. So yeah, I guess these are the principled limitations of this approach. And in what let's say scalability is concerned, yes, I guess that like all verification tools may at some point stop scaling as the inputs grow larger. And this is basically